Hello everyone, welcome back. In this lecture, we are going to discuss the relationship between yield strength in shear to yield strength in tension, or ratio of SYS over SYT, or you can write sigma YS over sigma YT. So first of all, we'll revise our last lecture. In the last lecture, we discussed about the theories of failure. So first was maximum principal stress theory, MPST, that gives the good prediction for brittle materials. So because brittle materials are weak in the tensile test, normal stresses, tensile stresses or compression stresses in comparison to shear stress. So this theory gives good result for the prediction of failure of brittle materials. So this is used for brittle materials. And second, we studied about maximum shear stress theory, MSST, that this theory is used for predicting the failure of components made of ductile materials like transmission shafts, because ductile materials are weak in the shear and in comparison to strength, their strength in the tensile or normal stresses. And third was the maximum principal strain theory, MPSTT. No, this theory is not recommended because this gives the reliable results in the particular cases only. So at the end of this lecture, we are going to discuss about this type of case. And the maximum, next was the maximum strain energy theory, or MSET. This may be used for the ductile material. And last was the maximum strain energy theory, or distortion energy theory, or you can say Mises and Tresca's theory. This theory is the best for ductile materials than any other theories of failure. So in one go, we can say the first one is used for brittle material, rest 2, 3 and 4 are used for ductile material. But for the ductile material, best one is maximum shear strain energy theory. So now we'll take a case of torsion test or pure shear stress. So in torsion, let's consider one shaft which is subjected to pure torsion. So if we take an element at the surface of this shaft, because the surface of this shaft will be experiencing maximum shear stresses, because shear stress along the radial distance of this shaft is varying linearly, and the shear stress maximum at the outer surface. So if we take the critical component which is at its outer surface and draw the state of stress, that would be something like this. This is the state of stress when the shaft is subjected to torsion or pure shear stress. This is pure shear condition. So in this condition, if we find out the principal stresses, so those stresses would be tau and minus tau. So this is major principal stress and this is minor principal stress. So sigma 1 and sigma 2 is equal to tau and minus tau. So if we draw this diagonal, so along this diagonal there would be a tensile stress tau, or which is positive tau, because the tensile stresses are written as positive. And along this diagonal there would be a compressive, or this is sigma 2, which is minus tau. So in the pure shear stress case, the principal stresses are tau and minus tau. So now when the component is subjected to pure shear case, so tau, in this case tau must be, or we can say tau is equal to 16t over pi d cube. And if we, for the safe design, we can say, for safe design, we can say tau must be less than tau permissible, and tau permissible is SYS over factor of safety, or we also can write sigma ys according to our nomenclature. So tau must be less than or equal to sigma ys over n. So now we'll take all the serial wise all the theories, and we'll discuss the relationship between sigma ys and sigma yt. So first we'll consider the MPST, maximum principal stress theory. Maximum principal stress theory. So according to this theory, sigma 1, in the last lecture we discussed, sigma 1 must be or less than sigma yt over n, and in the case of pure shear stress, sigma 1 is tau, so we can say tau must be less than or equal to sigma yt over n. Here n is factor of safety, n is factor of safety. So, or this tau permissible, we can say this is sigma ys over n must be less than or equal to sigma yt over n. So this can be cancelled out. So we can say sigma ys is equal to sigma yt, or sigma ys over sigma yt is equal to 1. So in the case of maximum principal stress theory, the ratio of the yield shear strength to the yield tensile strength is equal to 1. So now we'll take the next case of maximum Mssd. So this is maximum shear stress theory. So according to this theory, we know that tau max must be less than or equal to sigma yt over 2 multiplied by n. N is factor of safety. So in the case of pure shear stress, so or tau max can be given as sigma 1 minus sigma 2 divided by 2. This must be less than or equal to sigma yt over 2 times multiplied by n. So in this case, we know that sigma 1 is tau and sigma 2 is minus tau divided by 2 sigma yt over 2n. So this 2 will cancel out with this 2, and we can say this is 2 times tau over is equal to or less than sigma yt over n, and this tau is sigma ys over n. So sigma ys over n, sigma yt over 2 times of n, this 2 comes here and this n will get cancelled out with this n. So we can say according to this theory, sigma ys is equal to sigma yt over 2, or we can say sigma ys over sigma yt is equal to 0.5. So according to maximum shear stress theory, we can say the sigma ys and sigma yt is, the ratio of these two is 0.5. And next theory is MPST, maximum principal strain theory. So next is maximum principal strain theory, MPST. So according to this theory, we know that sigma 1 minus Poisson's ratio sigma 2 must be or less than sigma yt over n, or we can say, so in the pure shear stress case, sigma 1 is tau minus mu and sigma 2 is minus tau. So we can write sigma yt over n, or we can say tau 1 plus mu is sigma yt over n, or we can say tau is equal to sigma yt over 1 plus mu multiplied by factor of safety n, and this tau is sigma ys over factor of safety. So this is sigma ys over n, sigma yt over 1 plus mu, and this is n. So this n will get cancelled out, or we can say sigma ys is equal to sigma yt over 1 plus mu. Or if we take mu equals to, we can say if mu equals to 0.3, Poisson's ratio is 0.3, then we can say sigma ys is equal to 0.775 times of sigma yt. So this is the ratio of yield strength in shear to the yield strength in tension according to maximum principal strain theory. So, and next theory is total strain energy theory. Total strain energy theory. So according to this theory, we know that sigma 1 square plus sigma 2 square minus 2 times Poisson ratio sigma 1 sigma 2 must be less than or equal to sigma yt over n whole square. These all we had derived in the last lecture, so before this you can go or watch that lecture, and we are having this type of relation. And in the pure shear stress case, as we know that sigma 1 is tau, so this is tau square, and this is minus tau, so minus tau square, 2 times Poisson's ratio tau multiplied by minus tau, and this is sigma yt over n whole square. If we solve this, this becomes 2 times tau square 1 plus mu is less than or equal to sigma yt over n whole square. And we can say tau square is sigma yt over n whole square multiplied by 1 over 2 times 1 plus Poisson's ratio. So if we take the tau equals to, so sigma yt over n multiplied by 1 over under root 2 times 1 plus mu. So this tau is sys, so we'll write here this tau is sigma ys over n must be less than or equal to sigma yt over n 1 over 2 1 plus mu under root. So this n will get cancelled out, and the relationship becomes sigma ys is equal to sigma yt over under root 2 1 plus mu. So if we take, if mu equals to 0.3, then this sigma ys is 0.625 times of sigma yt. So this is the ratio or relationship between yield strength in shear to yield strength in tension according to maximum strain energy theory. And so next we'll take the next theory, maximum distortion energy theory. So according to that, according to this theory, we know that sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2, this is sigma yt over n whole square. So from here we know that sigma 1 is tau, so this is tau square, this is minus tau square minus 2 tau multiplied by minus tau, and sigma yt over n whole square. So if we solve this, this becomes 3 tau square sigma yt over n whole square. Or from here we can say tau must be less than or equal to sigma yt over under root 3 n. N is factor of safety, so this tau is sigma ys over factor of safety n, so this is sigma yt over under root 3 n, so n will get cancelled out, and from here we can say sigma ys is equal to sigma yt over under root 3. So we can say sigma ys is 0.577 times of sigma yt. So this is the relationship between the yield strength in the shear to the yield strength in the tension using the or according to maximum distortion energy theory or Mssd and so Mssd theory. So this is the relationship between sigma ys is equal to sigma yt, or in the summary if we can say, if we make one table, this is serial number, this is theory of failure, and this is sigma ys over sigma yt, and we can make our comment. So first one is MPST. According to this ratio is 1, and we can make one comment, most economic but unsafe for ductile. So but unsafe for ductile material. So as we discussed, this theory is used for brittle material, and this is second, and one is MSST. So according to this ratio is 0.5, and we can say that this is oversafe and uneconomic. And third one is MPST, maximum principal strain theory, and according to this is the 1 over 1 plus mu, and for mu equals to 3 we find out this ratio is 0.77. And fourth was total strain energy theory, total strain energy theory. For this was the 1 over under root 2 1 plus mu, and for mu equals to 0.3 this relationship was 0.625. Otherwise we have to remember these formula, because in the exam they will directly ask you the relationship between or ratio of these two, or if they given the Poisson's ratio, so according to that Poisson's ratio we can calculate our calculation. So if we remember this, that would be beneficial. And fifth was MDT, maximum distortion energy theory. So according to this was 1 by under root 3, or you can say 0.577, and this is most economic or most favorable for ductile material. So this is all about the theories of failure for calculating the ratio of yield strength in shear to yield strength in tensile. Now we'll take the special case where we have to choose the particular theory to find out the answer. So if we are having one case or something, suppose this is our component, This component is subjected to sigma, sigma, and sigma. So in all the direction there are equal and of the same nature stresses. So in this case one can ask, if problem is asked something for the state of stress, for the state of stress given in this figure as shown here, which of the following theories of failure is used. Theories of failure is used, and you are given with options like first option can be A, MPST, second option can be MSST, and third can be like MDET, or fourth can be given as B and C, and fifth can be given as A, B, C, and D. All of the above can be used. So in this is now we'll make one statement. This is very important. So here we have to say that MSST and MDET, maximum shear stress theory and maximum distortion energy theory, cannot be applied when principal stresses are equal in magnitude and are of same nature. Means all the principal stresses are equal in magnitude and same nature, means either all of the stresses are compressive or all of the principal stresses are tensile and having same magnitude. So in this case we cannot apply the MSST and MDET. So what we have to do in this case, so in such cases best theory is MPST, maximum principal stress theory, and MPST. So we can write one more statement under triaxial state of stress. If MSST and MDET can be used when principal stresses are either different in magnitude or different in nature. So if we are having this type of problem or we are facing this type of situation, then we have to very careful while choosing the theories of failure to apply to design the component. So if the situation is something like this, all the principal stresses are equal in magnitude and of same nature, so we cannot apply the MSST or MDET. So MSST in the triaxial cases, MSST or MDET only can be applied when the principal stresses are either of the different magnitude or different in nature. So this was about the ratios of the yield strength to the in the shear and yield strength in the tensile, and this was the one special case where we have to be careful while applying the theory of failure. Thank you.